Hey guys, this is Mrs. Gastler, and in this video we're going to talk about types of collisions. So, it's not that hard. We're just going to take a couple of things that we already know and apply it to collisions and identify a couple of different types. Actually, there's 3 types, 1, 2, 3. And I've got a spectrum here because there's actually kind of a spectrum, and then there's particular things that, that we're going to talk about. And so when we talk about the type of collision that two things running into each other is, it's always based on what happens to the kinetic energy. Okay, so when you're looking at two objects running into each other, so you've got object A and object B, and maybe they're coming toward each other, maybe B and A are going in the same direction and one runs into each other, like rear-ending. A car rear-ending another one, but either way, they're bam, okay, they just ran into each other, bam. And maybe they bounce off, maybe they stick together, maybe they bounce off, but they continue going in the same direction. All sorts of interesting things can happen. Maybe they hit at weird angles. You can have 2-dimensional collisions and 1-dimensional collision. If you have, more than one object, you can end up with 3-dimensional collisions. All sorts of interesting things can happen. You can even have 4 objects involved in a collision. It gets pretty complicated out there, really. You guys really have to know about 1- and 2-dimensional collisions. You don't have to do a lot of calculations with 2-dimensional collisions, but you need to understand what's happening so that you can describe and answer questions about those. So we'll talk a little bit about that. The first kind of collision is called elastic collisions, and those go in the middle. And there's one that goes right on this line here. I'm going to turn it. It is called a perfectly elastic collision because there's some collisions that we consider to be elastic, even though they're not perfectly elastic. In a perfectly elastic collision, the kinetic energy, the total kinetic energy before is equal to the total kinetic energy after. Okay, so the initial total kinetic energy and the final total kinetic energy are equal. Okay, in the real world, perfectly elastic collisions don't really exist. If you've taken chemistry, there's this thing called an ideal gas, which also doesn't really exist. But those particles bounce off of each other, and every time they have a perfectly elastic collision because there's no loss in energy or gain in energy when they run into each other. And so we can know some things about the gas particles. We can assume a bunch of collisions are nearly perfectly elastic, but they're not really. So in an elastic collision, which might be this, range around here, the kinetic energy total before is about the same as the kinetic energy after. In reality, some energy is usually lost, okay? If we go to the lost end, which negative numbers for me usually go on this side, so I'm going to put that over here. We call those inelastic collisions. Inelastic collisions. And truly, anything off of this line where energy is lost is inelastic. So once you're no longer conserving kinetic energy, and once kinetic energy is not the same, you are in the realm of inelastic. And then the more energy you lose, the more inelastic it is. And then here's what's really kind of annoying. A perfectly elastic collision doesn't mean you've lost all of the kinetic energy. Whoops, knocking into stuff now. But a perfectly inelastic collision just means that the objects have stuck together. Okay? So when you have, maybe you've seen this, when cars crash into each other and their front ends get tangled together and now they're like stuck and they're moving however direction they're moving. They're still moving, so they have kinetic energy. They haven't lost all the kinetic energy, but they're stuck together. That makes it a perfectly inelastic collision. So if you read in a problem or somewhere it says a perfectly inelastic collision, you know that the objects are stuck together, okay? They have not lost all the kinetic energy, they're just stuck together, okay? perfectly inelastic collision. Okay, anywhere in between there, you've lost some amount of energy. So we might make a little note. Some kinetic energy is lost. Okay, anywhere, there we go. Anywhere in there, some kinetic energy is lost. Now, on the other side, energy is lost. Over here, we have some amount of energy is gained. Now, in order to do that, there has to be some device or thing that is adding energy into the system, okay? So there is something adding energy. In some of the examples in the book, it's a firecracker. Sometimes it's like a spring-loaded thing, like in the lab. Somebody had the carts have a little plunger in it. You boop, push the plunger, and the little spring pops out and pushes the carts away. So that's something adding energy. Okay, so in that situation, these have a fun name. These are called explosive collisions. Okay. These don't have to start at rest. You could just have like a conveniently positioned thing that just happens to fire or push or something right at the right time so that there's energy added at the right time. But we're adding energy. Okay, we're adding energy in this situation. There is not a perfectly explosive collision, so I'm not going to add anything there. But what we need to know, and I wish I had another different colored pen, but I don't. I'll write with this one. Maybe it's different colored. Is that a different color? I can't tell. All right. When we're talking about collisions, we also have that conservation of linear momentum. That is always true. Okay, no matter what kind of collision it is, the conservation of linear momentum is always true. So I find it's most useful to write that in an inelastic collision, the total momentum before is equal to the total momentum after. And in any inelastic collision, sorry, my words are getting stuck together, the total momentum before is equal to the total momentum after. And that's true over here. The total momentum before is equal to the total momentum after. And that's true right here. The total momentum before is equal to the total momentum after. Now, if you're like, I'm going to remember that, then go right ahead and don't write this down. But the total momentum before is equal to the total momentum after. No matter what, the momentum is the same before and after in any kind of collision. It's the kinetic energy that changes, okay? You can only use the kinetic energy as being the same in a perfectly elastic collision. Okay. Now, in your textbook, if you see elastic collision, you can say, okay, it's pretty much the same, and you can write that they're the same there too. Okay. And we're going to do a couple of, what do you call it? Examples. Okay. So when we use this information, we can use this information really well in calculations or solving problems with letters. Okay, that's where you calculate and you just don't know the numbers. You just are solving for X or Y or V or B or whatever letter it's asking you to find. And so I have two examples that we're going to do. This first one, example one, we have a ball with a mass of 0.44 kilograms. It's moving east at 3 meters per second. I'm going to draw this. Here's our ball. It's going east at 3.3 meters per second. It collides head-on with a 2.2, this is 0.44, and with a 0.22 kilogram ball at rest. The collision is perfectly elastic, so K initial equals K final. Yeah, what speed and direction will each ball have? That should really say have. Have. No, it says what will it be? Erasable pen. What will the speed and direction of each ball be? There we go. After the collision. Okay, so this is initially at rest. So I'm going to write 0 meters per second. Okay, so if I want to solve this problem, I need to write down two things. Okay, so I've got my momentum, my P total before equals my P total after. And before, the only guy that's moving is this one, so I'm just going to leave that one off, or I can write it down and then note that it's 0. So my M1 V1 initial equals, plus M2 V2 initial, and that's 0, equals M2 V2 final, plus M1 V1 final. I switched those. Sometimes that happens. And I also know that the kinetic energy is conserved. So K1 initial plus K2 initial equals K1 final plus K2 final. Okay. So that's going to be 1/2 M1 V1 initial squared plus 1/2 M1 2 initial squared, but that's 0, equals 1/2 M1 V 1 final squared plus 1/2 M2 V2 final squared. Okay. And if you don't like solving problems, you're probably like, crap, I don't like this. You know, but it's not so bad. The first thing I'm going to do is get rid of all these halves because everybody's got one. So nobody cares. Haha. Well, somebody cares, right? Okay, so, and I can plug some numbers in, or I can leave it this way, right? So I know these numbers, and I know some of those numbers, right? But I can't really do a whole lot here. So let's see, M1 V 1, you know, I might feel better if I put some numbers in here. Okay, so 0.44 times 3.3 equals I'm going to switch those in my head here. 0.44 V1F plus, that's a vector, 0.22 V2F. And then I've got 0.44 times 3.3, whoops, that's a 3, squared equals 0.44 times V1F squared plus 0.22 times V2F squared. Okay. And now in algebra, you probably have learned numerous ways to solve two equations and two unknowns. This one's got a squared in it, and this one doesn't. So I would probably choose substitution. So I would solve this one for V1F or V2F, and then plug it in over here, and then solve for the other squared. Which, since it's just one unknown, or two unknowns, I don't have to do any fun factoring. I know people love to factor, or quadratic formula or anything like that. I don't need to do that. Although you might actually be able to just do that over here, right? Don't. Yeah, let's just not do that. You could. I know some people who might try. V1F, let's see, if I move everything around, I'm just going to do that on my calculator here. 0.44 times nope. I need a bigger calculator. That one's dead. 0.44. 3.3 minus 0.22. Yeah, I really need a different calculator. Okay, so I'm going to have 1.452 minus 0.22 V2F over 0.44. So that's what I'm going to stick in over here. And this is going to get kind of gross and ugly for a little bit, but hopefully you can see that eventually I'm going to come out with a V1F equals a number, and then I will be able to plug that back in over here to get a V2F. So it may not be very pretty, and maybe you don't like the algebra part, but eventually you'll have an answer there, okay? Now this next one, which is with an inelastic, well, actually, I think I just spoiled alert. The next one here is just a little bit easier. So example 2, we've got a 1,200 kilogram car traveling initially with a speed of 25 meters per second. I'm going to go ahead and draw this. This way, that's a car, right? Okay, 1,200 kilograms, and it's going 25 meters per second to the east, and it rear ends a 9,000 kilogram truck that's going in the same direction at 20 meters per second. That's why they ran into each other, okay? Right after the collision, the car is going with a speed of 18 meters per second east. So it's slowed down 18 meters per second, but it still has the same mass, unless it drops in pieces. What is the velocity of the truck after? Okay, so this is conservation of momentum. P total initial equals P total final. Initially, we have the mass of the car plus the speed of the car, or times the speed of the car, mass of the truck times the speed of the truck initially, mass of the car times the speed of the car finally, plus mass of the truck, speed of the truck finally. Okay, so let's see, 1200 times 25 plus 9,000 times 20 equals 1200 times 18. I didn't draw the truck. Question mark, 9,000. Plus 9,000 times V truck final. So this only has one unknown, so it's just a matter of doing the calculation there. 1,200 times 25. That's 30,000. On my little 4-function calculator, I'm going to write that down. 9,000 times 20. Oh, that's a lot. 180,000. That's for a grand total of 210,000 kilogram meters per second before. We went down to wrong number, 21,600 kilogram meters per second after. We'll be dividing that by 9,000 to get VTF. Minus 21,600 divided by 9, 1, 2, 3. All right, so the truck afterward is going 20.9 meters per second and still east. Whoops, east. There's a T there. Okay. What kind of collision was this? So in order to answer that question, we need to know what happens to the kinetic energy. So I just need to find the kinetic energy of everybody. Kinetic energy of the car before, kinetic energy of the truck before, kinetic energy of the car after, and kinetic energy of the truck after. So 1/2 mv squared, 1/2 mv truck initial squared, and so on and so forth. This would be easier if I used Microsoft Excel, because then Microsoft Excel could do all the calculations for me. You wouldn't have the option to use Microsoft Excel. Whoops, that should be an F. On an AP test, you'd have to use your calculator. But if you had a better calculator than this one, you could do it definitely faster than me, because you could store numbers. And if you don't know how to store numbers, you can ask. This one is awful, though. All right, 25 times 25 times 1,200 times 0.5. That's 375,000. 9, 1, 2, 3 times 20 times 20. That's a lot. 1 million. These are joules, by the way. And then we've got, what did we go down to? 18 times 18. 1,200 times 0.5. 194,400. And, oops, come back. 20.9 times 20.9 times 9,000 times 0.5. 1965645. So the truck gained some energy, but the car lost a bunch. So overall, what happened? So 375,000 plus 180,123. So we started with 21,75000 and 194,400 plus 1965645 216,0045. So we have lost. That makes this inelastic collision. And so the last question, if it's inelastic, how much did the kinetic energy change? We just need to subtract those. 2, 1, 7, 5, 1, 2, 3. We've lost 14955 joules of kinetic energy. Okay. All right, so there you have it. There's a couple of things there. If you'd like to see me work out the rest of the math here to get to an actual answer, please let me know. If I did it now, it would take a long time, and this video is already long enough, so I'm going to stop there. All right. Thanks for watching. Let me know if you have questions.